Hi students, my name is G. Kishore Kumar, Assistant Professor, Electronics and Communication Engineering Department, Velagapudi Ramakrishna Siddhartha Engineering College, Vijayawada, Andhra Pradesh. In this video, we are going to see the basic concepts of circuit theory. So now first topic is Kirchhoff's laws. The entire study of electric network analysis is based mainly on Kirchhoff's laws. But before discussing this, it is essential to know the following terms. So the entire electric network analysis is mainly based on Kirchhoff's laws. So here we are discussing mainly node, branch, loop, mesh. Node. A node is a point or junction where two or more circuit elements meet is called node. So here circuit elements is nothing but resistor, capacitor, inductor. Simply node is nothing but connecting point of two or more elements is nothing but node. In other words, a point of connection between two or more branches is known as node. Okay. So if you see the example of electrical network, so here, so 5 ohms, 2 ohms, 3 ohms, 2 amperes, current source, 10 volts, battery are the branches. So here 3 branches, 2 ohms, 3 ohms, 2 amperes current source are connected to same point. So this connecting point is the node. So here this node is name it as node B. And also here 10 volt source, 5 ohms resistor are connecting one point. This connecting point is one node. So here name it as node A. Okay. Similarly, 10 volt source, 2 amps, 2 ohms resistor, 3 ohms resistor, 2 amperes current source are connected to one point. So this connecting point is one node. That node is name it as node C. Okay. Same explanation is written here. In the circuit above, we can list 3 nodes that exist inside it. There are nodes A, B and C. The 3 nodes connected to a single wire from a single node B. So another concept is branch. A branch is a circuit element such as voltage or current source or a resistor, capacitor, inductor. Okay. So branch is nothing but either voltage source or current source or resistor, inductor, capacitor. Okay. So in this figure, okay, branches are 10 volts, 5 ohm resistor, 2 ohm resistor, 3 ohm resistor, 2 amperes current source. Total 5 branches. So here total 5 branches. The circuit above we can see that we have 5 branches. So these 5 branches are 10 volts voltage source, 5 ohms resistor, 2 ohms resistor, 3 ohms resistor, the 2 ampere current source. So next one, loop. A loop is a closed path inside an electric circuit. Okay. So loop is nothing but closed path inside the electric circuit. Okay. So here there are 4 figures. So if you observe the figure A, okay, here 2 loops. Okay. So one loop is from A to B, E, F, A. Okay. This is one loop. Okay. So another loop is right side from B to C, D, E, B. So if you observe this figure B, so including 2 loops, so another loop is from A to F. A, B, C, D, E, F, A. So this is also one closed path from node A to from node B, C, D, E, F to A. Okay. This is also one closed path. So this is also nothing but one loop. Okay. Similarly, figure C also. Okay. Closed path from node A to node F. Another closed path is from node B to node E. So figure D is closed path from node A to node F. Okay. And two closed loops. This one is one closed loop. This one is one closed loop. So information from third loop is redundant. So third loop is not required here because already indicated this loop 1 and loop 2. Okay, no need to place the entire loop of this circuit. Mesh. Okay, next one is mesh. A closed loop which contains no other loop within it or a path which does not contain on other paths is called mesh. Okay. So here two meshes, mesh 1 and mesh 2. Okay. If you observe this mesh 1 is the one closed loop. Okay. This closed loop not contain any other closed loop. So that's why this one is one mesh. Okay. Similarly, for mesh 2 also, there is no closed loop inside this path. So that's why this one is one mesh. So here two meshes, mesh 1 and mesh 2. Okay. Mesh 1 and mesh 2 does not contain any other closed loops. Next one is Kirchhoff current law. The algebraic sum of currents meeting at a junction or node in an electric circuit is 0. Okay. So Kirchhoff current law is nothing but the algebraic sum of currents meeting at a point or junction or node is nothing but 0. I am put in another way, it simply means that the total current leaving at a junction is equal to the total current entering that junction. So the meaning of this point is the total currents leaving at a node is equal to total currents entering at a node. Okay. Simply entering currents, the sum of entering currents is equal to sum of leaving currents. Okay. So consider the case of few conductors meeting at a point A as in figure A. So in this figure, okay, observe the node A. Okay, so few conductors are meeting at a point A. Here conductors are I1, I2, I3, I4, I5. Some conductors have currents leading to point A, whereas some have currents leading away from point A. So here some currents are entering to node A, some currents are leaving from node A. So here entering currents are I1, I4 and leaving currents are I2, I3, I5. Assuming the incoming currents to be positive and the outgoing currents negative. Okay. So here assume incoming currents are positive, outgoing currents are negative. If you observe this figure A, the algebraic sum of currents meeting at a point A or node A is equal to 0. So here entering currents are positive, assume it as, and leaving currents are negative. So here entering currents are I1, I4. So I1, I4 are positive. Okay. I1 positive, I4 positive. And leaving currents I2, I3, I5 are negative. I2 negative, I3 negative, I5 negative. So sum of this algebraic sum of currents meeting at a point is 0. So that's why equate to 0. Now rewrite as I1 plus I4 minus I2 minus I3 minus I5 equal to 0, or I1 plus I4 equal to I2 plus I3 plus I5. Why it is I1 plus I4 equal to I2 plus I3 plus I5? So another definition is entering current, sum of entering currents is equal to sum of leaving currents. So that's why here write it as incoming currents equal to outgoing currents. Here incoming currents are I1, I4 and outgoing currents are I2, I3, I5. Similarly for figure A and node A, at node A, entering current I and leaving currents are I1, I2, I3, I4. Okay. So algebraic sum of currents meeting at node A is equal to 0. So entering current is positive and leaving currents are negative. So here leaving currents are negative means I1 minus I2 minus I3 minus I4 minus. So equate to 0 or entering current equal to sum of leaving current. Here entering current is I equal to sum of leaving currents I1 plus I2 plus I3 plus I4. Okay. And also express it as we can express the above conclusion, thus summation of I equal to 0 at a junction. So at a junction summation of currents is equal to 0. Next one is Kirchhoff voltage law. The algebraic sum of all the voltages in any closed circuit or mesh or loop is 0. Okay. So Kirchhoff voltage law is nothing but the algebraic sum of all the voltages in any closed loop or mesh is equal to 0. So if we start from any point in a closed circuit and go back to that point, after going round the circuit, there is no increase or decrease in potential at that point. This means that the sum of EMFs and the sum of voltage drops or rises meeting on the way is 0. So here Kirchhoff voltage law is algebraic sum of all the voltages in any closed path or mesh or loop is equal to 0. Okay. Starting from one point at a closed circuit. Okay. So if you observe this figures, figure A, in figure A, node is represented and the loop is represented, branch also represented. Okay. So extract the node part of the circuit from figure A, that is figure B, and also extract this loop from figure A, that is denoted in figure C. So figure B is representation for Kirchhoff current law and figure C is representation for Kirchhoff voltage law explanation. Okay. If you observe figure B, for this node, okay, all the currents are entering I1, I2, I3. Sum of currents in, okay, incoming currents. Okay. So sum of I1 plus I2 plus I3 equal to 0. Okay. That is assuming of all currents are entering. Suppose all currents are leaving, so some currents of outgoing minus I1 minus I2 minus I3 equal to 0. Okay. Now observe the figure C for Kirchhoff voltage law explanation. Already the definition of Kirchhoff voltage law is the algebraic sum of all the voltages around the loop or mesh is equal to 0. So this one is one loop or one mesh. Okay. So algebraic sum of all the voltages around this loop is 0. Okay. Some voltages counterclockwise order. Okay. So counterclockwise order means in this way, anti-clockwise direction. Okay. So now anti-clockwise direction from this point, V5 algebraic sum of voltage source V5 plus V6 plus V7 plus V8 equal to 0. Okay. In counterclockwise, that means anti-clockwise direction. Okay. Suppose clockwise direction minus V5 minus V8 minus V7 minus V6 equal to 0. Okay. So this is the explanation of Kirchhoff voltage law, and this is the explanation of Kirchhoff current law. Now determination of voltage sign. Okay. So my concentration is notation of the sign for batteries or voltage source. In applying Kirchhoff laws to specific problems, particular attention should be paid to the algebraic signs of voltage drops and EMFs. Otherwise, result will come out to be wrong. Okay. Without place the voltage signs correctly, it will give wrong result. Okay. So particularly placing the signs, okay, we concentrate more on placing signs of batteries or voltage source. So sign of battery EMF. A rise in voltage should be given a positive sign. Okay, rise in voltage should be given a positive sign. Here rise in voltage means from negative to positive. That means negative sign to positive sign representation of voltage source is rise in voltage. Okay, that represented with positive sign. If you observe this figure, this battery E is rising from minus to positive. Minus to positive means rise in voltage. So that's why place positive signs. That's why plus E. And a fall in voltage is negative sign. Okay, here fall in voltage. Okay, battery is, okay, fall from positive to negative. That's why fall in voltage. Okay, so represented with negative sign minus E. Keeping this in mind, it is clear that as we go from the negative terminal of a battery to its positive terminal, negative terminal of a battery to its positive terminal is shown in figure. Already explained these two figures. And there is a rise in potential, hence this voltage should be given a positive sign. So here rise in voltage, rise in potential, so positive sign. If on the other hand we go from negative terminal to positive terminal to negative terminal, so here positive terminal to negative terminal, then there is a fall in potential, hence this voltage should be preceded by a negative sign. So this voltage should be represented with negative sign, fall in voltage. Okay. That means positive terminal to negative terminal is fall in voltage, negative terminal to positive terminal is rise in voltage, represented with positive sign, and fall in voltage, that is nothing but positive sign to negative sign represented with negative sign. So it is important to note that the sign of battery EMF is independent of the direction of the current through the branch. Okay, current through the branch. It is important to note that the sign of the battery EMF is independent of the direction of the current through that branch. Okay, if you observe these two figures, current direction is same direction for both the cases, but representation of battery sign is based on the rise in voltage and fall in voltage, not based on the current direction. Okay, so that is represented here. That means independent of the direction of the current. Okay, independent of current direction. Battery sign indication is independent of current direction, not dependent on current direction. Okay, clear? Next, sign of IR drop. Okay, voltage drops at circuit elements. Here circuit elements is nothing but resistor, capacitor, inductor. Now take the case of resistor in this figure. If we go through a resistor in the same direction as the current, then there is a fall in potential because current flows from a higher to lower potential. Okay, so important point is current always flows from higher potential to lower potential. Okay, if you consider this current direction, okay, current flows from higher potential to lower potential. For this figure also, current direction is from node B to node A. So that means higher potential to lower potential. Current flows from higher potential to lower potential. Again, hence this voltage fall should be negative. Okay. If you observe again the same point, if we go through a resistor in the same direction as the current, then there is a fall in potential. Fall in potential. Okay, if you observe this figure, okay, this voltage, okay, fall from positive to negative. So that's why fall in potential. Hence, this voltage fall should be negative. Voltage fall should be negative. That's why represented with the minus V. However, if we go in a direction opposite that of current, then there is a rise in voltage. Okay. If you observe this second figure, okay, current direction is from node P to node A. Okay. So in this direction, if you observe voltage polarity rise from negative to positive. So the rise in voltage represented with the positive sign. Hence this voltage rise should be given a positive sign. So that's why positive sign. Okay. If you observe these two figures, if you observe first figure, okay, main important point is current is always flows from higher potential to lower potential. So that's why represented with this point positive sign and this point negative sign. Okay. Coming to voltage drop, okay, voltage is falling from positive to negative, means falling. So represented with the negative sign. That's why minus V. Okay. So voltage across this resistor minus R. Okay. So coming to this figure, now current direction is current is flows from node B to node A. That means current always flows from higher potential to lower potential. So here higher potential representation positive sign, lower potential representation negative sign. And voltage direction is this way from node A to node B. So node A to node B voltage direction representation, that means voltage motion representation, rising voltage. Okay, rising minus 2 plus means rising. So rising voltage representation is plus V. So voltage drop across this resistor is plus IR. It is clear that the sign of voltage drop across a resistor depends on the direction of current through that resistor, but is independent of the polarity of any other source of EMF in the circuit under consideration. So in the sign of IR drop representation, sign of voltage drop across a resistor is completely depends on the current direction. Okay. In case of sign of EMFs, okay, sign of EMFs is independent of the current direction. In case of sign of IR drops, okay, voltage drop across resistor C is depends on the current direction. Okay, it is clear. So now consider this example figure for explanation of voltage drops potential indication or voltage drops polarities indication. So consider the closed path A, B, C, D, A in figure. A, B, C, D, A of this closed path. As we travel around the mesh in the clockwise direction, different voltage drops will have the following signs. Okay. Voltage drops of this all the elements in clockwise direction. Okay. From node A to B, C, D and A. So in this direction of traveling. Okay. The direction of traveling is the clockwise direction. Starting from node A. Okay. So current I1 is flowing through resistor R1. Okay. So current always flows from higher potential to lower potential. So here higher potential means positive sign representation. Here lower potential is negative sign representation. Okay. Positive to negative means voltage drop is falling voltage. So that's why represented with the negative sign at voltage drop across resistor R1. So here voltage drop across resistor R1 is I1 R1, and also here falling voltage. Okay, because current I1 flows from higher potential to lower potential. Here higher potential is positive sign, lower potential is negative sign. So coming to voltage drop is voltage is fall from positive to negative. So sign is negative sign. So that's why fall in potential. Now coming to voltage drop across resistor R2. Here also I2 current is flows from higher potential to lower potential. Higher potential plus to minus. Voltage drop across R2 is I2 R2, and sign is negative sign because fall in potential. Coming to battery E2. Battery E2 is positive sign to negative sign. That means fall in voltage. So represented with the negative sign, that is minus E2. E2 negative sign, that is fall in potential. Next, coming to voltage drop across R3. Okay. So here current through R3 is flows from node D to node C. So that means current always flows from higher potential to lower potential. So here higher potential to lower potential. Higher potential means positive sign, lower potential means negative sign. But here we are consider the clockwise direction. So that means here positive sign, here negative sign for voltage drop calculation of R3. That means voltage is rising here minus to positive. Okay, rise in voltage. So that's why plus sign indicate for voltage drop of I3 R3, that is rise in voltage. Okay. Now coming to battery E1. Okay, in clockwise direction representation, minus to plus rise in voltage, minus to plus rise in voltage. So that's why positive sign for rise in potential. Okay. Now coming to R4 resistor. Okay. Current through R4 is I4, and this I4 current is flows from node D to node A. Okay. And current flows from higher potential to lower potential. So here positive sign, here negative sign. For calculation of voltage drop across R4, that is falling voltage. So that's why negative sign. I4 R4 is negative sign, that is falling potential. Okay. So now based on the Kirchhoff voltage law, get minus I1 R1. Okay. All the summation of all these minus I1 R1 minus I2 R2 plus I3 R3 minus I4 R4 minus E2 plus E1. The algebraic sum of voltages around the closed path is equal to 0 based on the Kirchhoff voltage law. So that's why sum of all the voltages are equal to 0. Okay. Now rewrite this equation: I1 R1 plus I2 R2 minus I3 R3 plus I4 R4 equal to E1 minus E2. So now consider the example. So in figure, the voltage drop across the 15 ohm resistor is 30 volts, having the polarity indicated. Polarity is already indicated. Find the value of R. So for this example, okay, calculate the value of resistor R. Okay. So already given voltage across 15 ohms resistor is 30 volts. Okay. Now calculate the current through resistor based on this voltage and resistor value. So coming to solution, current through 15 ohm resistor is I equal to voltage by current. Voltage by I equal to voltage by resistor, that is 30 volts by 15 ohms. So 30 by 15, that equal to 2 amperes. Next, current through 5 ohm resistor. Current through 5 ohm resistor. Okay. Already 5 amperes current is flowing through resistor. Okay. Already we have calculated current through this 15 ohm resistor is 2 amperes. Okay. These 5 amperes and 2 amperes are meeting at this point and leaving to this 5 ohm resistor. So this sum of these two currents are flows through 5 ohm resistor. So current through 5 ohm resistor is 5 plus 2, 7 amperes. 5 plus 2, 7 amperes. And the current through 5 ohm resistor is 7 amperes. Again this 7 amperes, you observe this 2 amperes is flows through this resistor and 3 amperes is flows through this resistor. Okay. So balance is 3 plus 2, 5. Here 7 amperes, 7 minus 5, 2 amperes. So again this 2 amperes is flows through this resistor R. Okay. So our calculation is correct. Apply KVL to this closed path. Apply this KVL to this closed path from 5 ohm resistor. So voltage drop across 5 ohm resistor is, if you observe, positive and negative. So fall in voltage. So that's why negative sign, minus 5 into 7, because current to this 5 ohm resistor is 7 amperes. So minus 5 into 7 and closed path in this way, clockwise direction. Voltage across resistor and also indicate positive sign and negative sign. Fall in potential. So here also negative sign, minus R into current through this resistor R is 2 amperes. So minus R into 2, and here voltage 100 volts is rising, minus to plus rise in voltage. So plus 100. Okay. And voltage drop across 15 ohm resistor is 30 volts. So positive to negative, fall in voltage. So negative sign, minus 30 equal to 0. So simplifying this equation, we'll get R is 17.5 ohms. So the value of resistor is 17.5 ohms. What is the voltage Vs across the open switch circuit? Okay. So for this figure, what is the value of the Vs? Now here we apply the KVL. So we will apply KVL to finding the voltage source Vs from starting from node A to B, C, D and to node A. So that means here clockwise direction from node A to node B. So here Vs, okay, clockwise direction, minus to plus, rise in voltage. So plus Vs, okay, and 10 volts, minus to plus, rise in voltage. So plus 10 volts. Again here 20 volts, plus to minus, fall in voltage. So negative sign, minus 20 volts. Again this 50 volts, plus to minus, fall in voltage, minus 50 volts. Okay. Again this 30 volts, minus to plus, rise in voltage, plus 30 volts. So that is equal to 0. Okay. Based on the Kirchhoff law, algebraic sum of all the voltages around the loop or mesh is equal to 0. So that's why the summation is equal to 0. So now simplify, we get Vs is 30 volts. So Vs is 30 volts. find the unknown voltage V1 in the circuit. Initially, one may not be clear regarding the solution of this question. One may think of Kirchhoff's laws or mesh analysis, etc. But a little thought will show that the question can be solved by simple application of Kirchhoff's voltage law. Okay. Taking the outer closed path A, B, C, D, E, F, A and apply KVL to get this equation. So here finding the unknown voltage V1 for this circuit. Okay. So before going to solve this problem, first we confuse whether we use Kirchhoff's laws or mesh analysis. But here simple solution is apply Kirchhoff voltage law for finding the voltage V1 by taking outer path. So by taking outer closed path from node A to B, C, D, E, F, A. From this outer path, here node C to D. Node C to D, current is 16 amperes current is flows through this 3 ohm resistor. In this direction, current always flows from higher potential to lower potential. So plus to minus. Voltage drop across this 3 ohm resistor is negative sign minus 16 into 3. Okay. Next, from D to E, there is no circuit element. Next, E to F. E to F. Okay. Current to this 2 ohm resistor is 4 amperes. Okay. 4 amperes current is flowing through this 2 ohm resistor. So current always flows from higher potential to lower potential. So here positive sign and here negative sign. Voltage drop across 2 ohm resistor is indicates negative sign. So minus 4 into 2. Okay. Next, coming to this node F to node E. Okay. So here 40 volts minus to plus, rise in voltage plus 40 volts, and voltage V1 plus to minus, fall in voltage minus V1, so equal to 0. So by simplifying this, we get V1 as minus 16 volts. Okay. The negative sign shows there is a falling potential. Okay. So negative sign indicates falling potential. Find currents in all branches of the network shown in figure. Okay. Find the currents in all the branches. Okay. Here we apply KVL. Okay. Finding all the branches in currents. Here we observe 1 ampere current is entering at node O. This 1 ampere current is and divided this node O to 2 ohms and 1 ohms, and also and this node A also divided, and here node B also divided, and finally total 1 ampere current is leaving at node C. Assume current through this 1 ohm resistor is X, indicate X. Already 1 ampere current is entering at node O, and current through 1 ohm resistor is X. So current through 2 ohm resistor is 1 minus X. 1 minus X. Okay. At node B. Okay. Node B to node A. That means current through 3 ohm resistor is, assume it as Y. So this 2 ohm resistor is 1 minus X. This 3 ohm resistor is Y. Okay. So finally this 4 ohm resistor current is 1 minus X minus Y. 1 minus X minus Y. 4 ohm resistor current. Okay. At node A. Okay. Node A, the Y and X are entering currents. These two currents are leaving at node A. So entering currents equal to leaving currents. That's why current through this 5 ohm resistor is X plus 5. Okay, finally 1 ampere current is leaving at node C. Apply KVL in this path and apply KVL in this closed path. Okay, my equations are observed. By solving these two equations, we will get all the branches in currents. Okay, now see the solution. Apply KVL to closed path of O, B, A, O. O, B, A, O. Here 1 minus X current is flowing through this 2 ohms resistor. Current always flows from higher potential to lower potential. So here positive to negative. That means voltage drop is falling potential. So negative sign, minus 2 into 1 minus X current, and again B to A. Okay. Current through 3 ohm resistor is Y. Okay. Here also plus to minus, falling potential for finding the voltage drop across 3 ohms resistor. So minus 3 into Y. Again node A to node B, because clockwise direction. So this current axis flows from node O to node A. Okay, higher potential to lower potential. For voltage drop calculation, here consider the clockwise direction. So minus to plus, rise in voltage. So plus 1 into X equal to 0. Okay. So now simplify this equation. You will get 3x minus 3y equal to 2. That is equation 1. Now coming to second closed path. Okay. Second, apply KVL to this closed path. A, B, C, A. Okay. A, B, C, A. From node A to node B. Okay. Current Y is flowing from node B to node A. Okay. So here clockwise direction. Current is higher potential to lower potential. For finding voltage drop, here minus to plus, rise in voltage, 3Y. Okay. Again voltage drop across 4 ohm resistor. This current through 4 ohm resistor is 1 minus X minus Y. Higher potential to lower potential. So negative sign indicate, minus 4 into 1 minus X minus Y. Again current through 5 ohm resistor. Okay. Here current is higher potential to lower potential, but voltage drop calculation minus to plus, rise in voltage, 5 into X plus Y equal to 0. Now simplify this equation. 9x plus 12y equal to 4. That is equation 2. By solving equation 1 and 2, we get x equal to 0.57 amperes, y equal to minus 0.095 amperes. Now calculate all the branches in currents. IOA 0.57 amperes. IOB means O to B 1 minus x 0.43 amperes. IAB means y. IAC x plus y. So x is 0.57 amperes, y equal to minus 0.09 amperes. IBC 1 minus x minus y. What is the potential difference between points x and y? The network. So for this network, finding the potential difference between x and y. Okay. Coming to solution. So first this closed path. Okay. So in this closed path, current is I1. Assume it as current I1. Already given 2 volts, 2 ohm resistor, 3 ohm resistor. So current I1 equal to voltage by resistor. Here voltage is 2 volts, resistances are 2 plus 3, 5 ohms. I1 equal to 0.4 amperes. Similarly for second closed loop. Okay, I2, okay, voltage by resistor 4 by 3 plus 5, 0.5 amperes. Now potential difference between x and y, that is Vxy, that is Vx minus Vy, Vx minus Vy. If we observe this closed path and this closed path, here current I2 is flows through this 5 ohm resistor, and also same current I2 is flows through this 3 ohm resistor. That means there is no current flow from this point to this point. This I2 current is not divided at this point. Okay. Similarly, for this closed loop, current I1 is flows through this 2 ohm resistor and 3 ohm resistor, and also this 2 volt source. Okay. There is no current dividing at this point, so here there is no current flow. Okay, in this path there is no current flow. By KVL from node X to node Y, that means this path. Minus 2 plus rise in voltage 3I1 from node X. This node X voltage is Vx, minus 2 plus rise in voltage plus Vx, and minus 2 plus rise in voltage 3I1 plus 3I1. Again this battery minus 2 plus rise in voltage plus 4 volts, here plus 2 minus fall in voltage minus 3I2 Vy, okay, plus 2 minus fall in voltage minus Vy equal to 0. Okay. Now simplify, Vx minus Vy equal to minus 3.7. So simply Vxy equal to minus 3.7 volts.